Hello, Calc BC students. This is Ms. Orloff. This is day 2 of 1.1. I'm finishing up the notes where Mrs. Saller left off. I hope you're all having a great day. And we are going to start with limits looking at like a visual. So we're going to look at a graph. And so I know that right here, this is my function. And that's a weird function, sine of x over x, correct? I mean, it's something we really haven't worked that much with. And we want to know the limit as it goes, as the function goes to infinity, negative infinity, and 0. Okay. We know that there's some issues with it going to 0, right? We know we can't divide by 0. We see that we have some things going on. So I've taken the liberty of already placing this in my graph. Now, you don't need to get this into your graph. You don't need to get this function into your graphing calculator at this time. You can just follow along and watch what I'm doing. But I did this, I have my mode on my calculator in radian mode, and I'm going to do my screen as zoom 7 for trig. Typically in calculus, I am not saying all the time, but the majority of the time, we are working in radian mode when we deal with trig. So that's something especially if you're a physics student, you want to make sure your calculator is in the right mode, right? In any case, I'm going to go ahead and show you the graph. So this graph is pretty neat, but we wanted to see out to infinity. So what I'm going to do, because my x max is -8 and, or I'm sorry, min is -8 and max is 8, let's make that a little bigger. What do you say? So let's do, I mean, -15 for sure is not negative infinity, nor is 15 positive infinity, but we might get a better visual. So we get this interesting graph. Kind of reminds me of an octopus. I don't know why, but it oscillates over that x-axis. And as it oscillates, it's getting closer and closer and closer to 0. And the one thing I love about this graph is I feel in previous courses, you're told, oh, you've got these horizontal asymptotes. And students tend to think graphs can't cross asymptotes, but they can with horizontals. They are behaviors. It's the behavior of the graph. And as x goes to negative infinity, the output y goes to 0. And x goes to positive infinity, the output of y goes to positive 0. Now, what happens when x goes to 0? As we learned from Mrs. Saller, for a limit to exist, the limit from the left must equal the limit from the right. I clearly can see that at 0. I see that occurring. As x approaches 0 from the left, y approaches 0. I'm sorry, y approaches 1. And as x approaches 0 from the right, y approaches 1. And if I zoomed in, I'd see a little hole there because this function is not defined at 0. But we also learned from Mrs. Saller that a function doesn't have to be defined at a value, at an x-coordinate, for the limit to exist. So I've taken the liberty to fill in that information. Those are limits that you have to know for now. There will come a time in this course where we could do them analytically, we could show those limits, but right now, those are limits you'd have to know. To extend a little bit on it, does it matter if I do x over sine of x, or does it matter if it's, for example, if I go back to my calculator and I say, well, okay, well, what happens if I do 4x? And let me be very clear, students. A lot of students will just put 4x in the denominator. It needs to be in a parenthesis. And I need to actually type 4 in to that denominator, right? So, will my limit values change? And the answer is no. Now that we know what these limits represent, what their values are, we can go ahead and look at problem 1. But what? Limit as x goes to 0 of tan x, tangent x over x. We've only been talking about sine of x over x. Well, one of the reasons I love calculus so much, I feel like it's the meeting, the gathering place of all the math you've learned prior. And for those of you who remember trig or pre-calc and you had to do trig identities, well, they are back. So I've got to think about it. And I know that tangent, excuse my horrible handwriting, can be written as sine of x over cosine of x over x. I also know that you are in calculus because you are mad, algebraic, awesome students. And so you would know that you can rewrite that as sine of x over cosine x, and we need the reciprocal of x, which is 1 over x. And from here, we know that multiplication is commutative. And we know our properties of limits. So we know we're going to have 1 times 1 over 1. So the answer is 1. The next limit, the limit as x goes to 0 of sine of 4 of x over x. Well, I know that what I really would like to have, I would really like to think about the limit as x goes to 0 of sine of a of x, where a is some constant, some real constant, a real number, over a of x. That's what I'd like to have. I don't have it. So I urge you to pause the video now and see if you can figure out what to do algebraically. Okay, so hopefully none of you are going to math jail. Math jail is where you go if you do some illegal math. And you realize that, well, sine of 4 of x over x is just an expression. And the only thing I can do to an expression is multiply it by a value of 1. I also know sine of 4x, 4x, that is the argument 4 times the value of x. It's a, if you want to think about it, horizontal transformations, it affects the domain, the angle. I cannot factor the 4 out. Please don't do it. So I have that. And so since this is an expression, I can only multiply it by 1. I'm going to throw a little blue in here now, a little nod to Miss Saller. Can't believe I'm doing this. I'm a diehard Sox fan. Mr. Dowell's going to be upset about this because I'm a diehard Sox fan. Mr. Dowell's a diehard Sox fan, and Mrs. Saller loves her Cubs. So I cannot believe I'm using some Cubs colors. Anyway, now I've done proper math. We do grade your work, so will the College Board. So if you do illegal math, you're not going to get credit. So don't do it. Okay. So now you're going to pause the video and do number 3 completely on your own. The next theorem, we're going to spend such a small portion of this class on it, but it can come up on an AP test. Our book calls it the sandwich theorem. When I was in college, it was called the squeeze theorem in the textbook I used. But nevertheless, you'll get the point. The sandwich, something between the squeeze, you're squeezing something. So we've got this function f of x. We have a function h that its outputs are either greater than or equal to f, and we have this function g which outputs are less than or equal to f. And what this is saying, if you go ahead and read this, if I can't find a limit directly, then maybe I can find it indirectly, and this is that case. So because of how h, f, and g are defined, the values, and I hope you understand in math when we say values, the outputs are squeezed between the two functions. So that means that whatever the limit of h is at c, if it equals the limit of g at c, well, guess what? The limit at f is going to equal that. So with that being said, I'm going to move on to the rates of change. And if I have time at the end of the video, maybe I'll give you a visual. However, if I don't have time, your book does a really good example showing you a graph of how they found the limit at some value of c of x squared sine of 1 over x. And so you should go ahead and take a moment and look through your book on that. Rates of change. You think of, oh, I'm going to find the rate of change, a slope. That's Algebra 1. Got news for you. That's calculus in a big way. And so we're going to talk about two things. We're going to talk about average rate of change versus instantaneous rate of change. The concepts aren't super hard, but again, it's something in calculus that kids tend to get a little bit twisted up as we apply to something more challenging. So a ball slides down a ramp so that its distance s from the top of the ramp after t seconds is exactly t squared feet. So I want to think about it as this function. And I want you to pause the video and finish this table. Okay, got my table, but I want to know average rate of change. And in this case, I want the speed. I want the speed of the ball, okay? Because all my outputs are positive. We're going to do speed. And I wanted it for the first 3 seconds. So I want change in position over change in time. So change in position over change in time. Students mess up, they'll do change of velocity over change in time. Always think about your units. Feet per second is what I should end up with. And so if I go ahead and do this, I should end up with 3 feet per second. So in the end, I got the average rate. But is that the rate at 3 seconds? At the moment of 3 seconds, what is the speed? And how could a good estimate be found? And how could an exact answer be found? So we have to go ahead and find a method to do this. So if I found the rate of change between 3 seconds and 3.1, is that the instantaneous rate of change? So if I said I want s of 3.1 minus s of 3 over 3.1 minus 3, is that instantaneous? The answer is no. This is just an average rate. And if I went from 3 to 3.01, is that instantaneous? No, it's not. The only way I can get instantaneous rate of change is by thinking about, well, what if this point was, okay, so this is 3 plus h, comma, s of 3 plus h. And then I know the average rate of change, that doesn't look great, is the slope of the secant line. So this would still be the average rate of change. This is still average. There's one little thing, one tiny little thing that will make this ratio an instantaneous rate of change. And that, my friends, that's the limit as h approaches 0. If I look at the graph, h is the distance this green point is from the red point in the x direction. I want that distance to collapse, and what I'm looking for, and this is going to be really fast and sloppy, I'm looking for a tangent line slope. And that brings those 2 points, the red and the green, the limit makes them fall on top of each other. That's it for today, guys. If you have any questions, make sure you contact us. Have a good one.